Okay, so that's where we were. And this is enough stuff for 4 more hours, but you know. So recently, this is over the last 3-4 years, maybe, we came to realize that especially the liquid toner 2 phase is very fragile and also metastable. So to the left, you have fragility, and to the right, you have metastability. And so fragility, by this, we mean that any amount of quenched disorder, even super weak, will break the toner 2 equation. And that is what I want to talk most, because this is active matter in complex environments. That's why originally I thought that I have something to say. So this is actually a separate PowerPoint file that I prepared for today. It's also any amount of rotational anisotropy. If your space has some slightly easier directions, even super slightly easier directions, this changes the toner 2 thing into something that is more activizing-like, etc. For those of you who know what I mean, it's fine. If you don't know. That's actually making a qualitative difference. And somebody asked about chirality. Any amount of chirality disorder destroys the toner 2 phase. I may show you this because somebody asked briefly. Now, metastability this is adding something to the Vicsek model in some sense here in this context. This is just considering the Vicsek model a little bit more, or variants of it. So, for example, constant density flux. So if you take the toner 2 equation and you say, okay, density is because the particles, you know, the density is regularized, because they die and multiply at some fast time scales. I can enslave the density field. I have only which is constant, and I have only a velocity field description. So the toner 2 equation, where I set rho equals constant without incompressibility, or constant density flux. This equation, the ordered phase, the toner 2 phase, the moving phase, is metastable. I may show you this in a minute. And for toner 2 Vicsek flux, I will show you what happens if you put an obstacle, etc. And or even activizing flux. So I will show briefly these 3 things, and then switch to quenched disorder. Okay. All right. But if you ask too many questions about the first 3 things, you will never get seriously to the quenched disorder. It will be your fault. Okay, so let me do it myself. Maybe I can do this. Touch. No, higher. Okay. Yes, no, yes. Okay, anyway, so imagine my particles, my Quinker rollers or whatever, they're not perfectly spherical, so they have some kind of shape problems. Some of them turn left, some of them turn right on average, you know. Globally, it's okay, you know. So each particle has an intrinsic chirality, so the tendency to turn left, tendency to turn right. On average, it's 0, but each of them has one. So you can model this, but what should be called a Kuramoto-Vicsek model. So here is a Vicsek model and continuous time now. So positions evolve at speed v0. Okay, fine. Along an axis theta I. This theta I is ferromagnetic alignment, you know, synchronization with orientations of the nearby particles. So this is really the alignment term in Vicsek in continuous time. Some noise, rotational noise, of course. And here you have an extra thing, which is a constant omega I assigned to each particle I forever. which, should be zero in the Vicsek, is zero in the Vicsek model. And the question is now, if I have a distribution of these omega i's centered and with mean zero, so globally you have no chirality, but each particle has a chirality, maybe a very small omega I, but still something. What happens to Vicsek, to a Vicsek model? Okay. So this looks exactly like a Kuramoto model with noise, except that the coupling is local, and of course the particles are moving at constant speed along theta I. So yes.
Sir, is Markovian nature is inbuilt in this Vicsek model? The Markovian nature?
Well, this is assigned forever. This is a population, a disordered population of particles. Each of them has a given omega I, which does not change in time. So in some sense, I'm not sure what you mean by Markovian, but it's not Markovian because the particles keep memory of their chirality over time. Is that your question?
So in literature, generally for white noise, the dynamics actually a bit Markovian. So
the noise here is always white. There's this white Gaussian, etc.
So it's a bit Markovian in nature.
Yes, I mean, with omega I equals 0, this is a Vicsek model. And if you if you want to know, it's Markovian dynamics for sure. If you introduce this omega I assigned to a particle forever, then it's a disordered system in the sense of a Kuramoto model. Okay, so now we take the omega i's from a zero mean distribution with a width omega 0. Okay, and the question is, what happens if omega 0 is not 0, of course? And what happens is that, okay, so here you have, this is the case, yeah, this is a Vicsek case. As a function of a noise here, it's called dr now instead of eta, but it's the noise, okay, strength. And here omega 0, and the other parameter, the density has been fixed at 1, probably, something simple. So if this is a log scale here in omega 0, so to the left, you have Vicsek behavior, so the disorder, the gas, the bands, the liquid, okay, as you decrease the noise at fixed density, remember here? But then here you see that for omega 0, more or less like this, these things break. This is at fixed system size, okay? Break to be replaced by some mixture of bands and vortices, and here's some vortices. Anyway, this is at fixed system size. So you see that at a fixed system size, it takes a finite omega 0 to break the liquid, to break the bands. And the further question is, if I increase system size, what happens of this boundary? Okay. So what you see here is that we are looking at this boundary here between liquid and vortices. Okay. And we follow at fixed, let's say at fixed noise now, let's say here, at this point, and we look at how this point moves as we increase system size. Okay. And it moves like this. This is omega 0 star as a function of system size. It decreases like a power law. Okay. And if I extrapolate this result bravely, the conclusion is in an infinite system, any amount of chirality disorder, any small omega 0 non-zero will break the polar liquid. And okay, in that sense, the toner 2 liquid is fragile to chirality disorder. This can also be found at hydrodynamic level. We can derive equations in a chiral case with a distribution of chiralities, etc. And then we can show that the polar liquid is linearly unstable at mean field level, deterministic level. So in this case, it's easy. Also at continuous level, we have evidence. So this is a case where now these polar vortices and bands, etc., are very interesting, but not for today. So the message today is that any omega zero, however small, if the system is large enough, will break the Toner 2. Now, another remark, which is not shown here, is that the bands, on the other hand, and the bands will resist. So this boundary here, or here, whatever, between the bands and the vortices, this boundary decreases a little bit with system size, but stops. So asymptotically, the bands are more robust than the Toner 2 liquid, okay, to that sort of disorder. All right. Yes, this is easy. So this is a Toner 2 equation, which of course you remember by heart. Think Navier-Stokes, think Ginzburg-Landau, mix the two, you have Toner 2. Now, fix the density to a constant, so you don't have to worry about conservation of density because it's constant. You don't have to worry about pressure, it's zero. Okay, that's all. Simulate this PDE. It has an order-disorder transition at the deterministic level, but with noise. Now you put a bit of noise, okay? Now, in the ordered phase, no bands, by the way. The bands are only possible in a compressible system in which order and density are intimately coupled. If you kill density, no space for having bands, of course. So you only have disorder and order, okay, right? You put noise. And John Toner says that in this case, the 1995 calculation, supposedly exact at all orders in perturbation theory, in this case, the calculation holds because the symmetry I was talking about that is present in 2D, in this case, when you do the same calculation, you only have to deal with the velocity related vertices in RG, and not any of them with density because density is gone. So the exact results of the RG hold in this case. So we know that there is scaling, anisotropic scaling of the ordered phase, etc. At least that's what is claimed. And now, naively, I don't tell you why we looked at this because it's exact. Why would we look at this? Anyway, so if you simulate the ordered phase, now this is an initial condition of a PDE with noise, and the color is the orientation of the only field that you have, which is velocity. So, and this cyan color is 0, meaning going from left to right. Okay, now that's the initial condition. We put some noise and we watch. Gonna work this way. So this is Toner 2, so to speak. Whoops, up, something happened. Something else happens, etc., etc., etc. This is a case where this happens rather fast, although you don't know, this is not so fast. And now the steady state is really this form of Astor defects surrounded by shock lines or whatever, phase jump lines, okay? So the moving Toner 2 phase with its supposedly exactly known scaling exponents at all orders in perturbation theory, etc., breaks down. There are fluctuations that kill the phase and by nucleating these defects, and then you have this form. And this will, of course, never recover back to the ordered phase. And this happens everywhere in parameter space. So yes? Well, very good question again. Looking at what happens when it happens in a stochastic context like this is difficult. We are not quite sure. One thing is clear, it's not difficult in this case to nucleate this phase. It's spontaneously some, almost Astor-like configuration, because once you have a seed of an Astor, it will grow and invade. And you see, if I stop it at the very beginning, you get an idea, but I'm not sure it helps much, but at least you see how it starts. You see here, you see, you know, and so on. Okay, here nothing, here. So you have sort of a half shock line here and a small, you know, aster thing, and this thing will grow. And then what we also know is that along these shock lines, you have a higher probability of nucleating. That we can measure, so we know for sure. So once you nucleate one, you have an avalanche of, but of course you have one here also. Sometimes it dies out, you know, you see here.
Actually, we actually see this very similar stuff in the continuum model also.
This is continuum.
This is continuum?
Yeah.
Oh, okay.
We can do it. We have a microscopic model that does this too, but this is continuum.
I see. Okay.
Yeah. Sorry. This is the PDE, yeah. But we have a lattice model that does this. Okay, so here the lesson is, okay, you have this nice ordered phase. Supposedly we know everything about it. Unfortunately, all this knowledge is perturbative. And even at all orders in perturbation theory doesn't mean you have a whole answer, of course. So here, fluctuations that are not accounted for in perturbation theory cannot be accounted for in perturbation theory, probably. Nucleate these things, and this is dominant solution of gas of asters. And most of the activities, it's interesting because if you look at the dynamics, at larger times, most of the activity is at the intersection of these shock lines. You know, see here, 1, 2, 3. This is a very fragile area which will nucleate new asters. These are stable structures. Actually, there is work by Vafa in particular showing that these asters are the most stable +1 vortices in this system. So they are stable. These are stabilizing centers. And all the remaining activity is along the shock lines, and in particular at the intersection of the shock lines. That's where you nucleate new asters which grow and push the existing ones away, so to speak, in some sort of constant remodeling. Okay, so the message is metastability here. Yes?
So when I look at the video, so it looks like something's branching out, or I mean, look like branching out. So something's. If you can play it again.
I'm not sure I understand your question.
Looks like a branching instability kind of.
Branching?
Yeah.
Space-time, you mean?
Yeah.
Again, the new objects, the new asters are nucleated here. You look at the movie. If you have a good eye, you will see it. It's a bit fast, actually, but you see that there is a lot of activity and new asters nucleated at these intersections, and then they may grow or not, actually, and remodel the whole thing. So I'm not sure what you mean by branching process, but
Okay, maybe I mistook it. When I looked at the beginning, it appeared to me like something is coming and branching out into different fractal-like.
Well, this is not fractal. The distribution of these sizes here is of a correlation length. Correlations are quite normal. There's a well-defined typical size of these asters because when they are too big, they are susceptible to be invaded by others. That's why we understand, at least. So this is, you know, a large correlation length here, you know, a few hundreds typically, but a finite, well-defined correlation length.
Thank you.
No fractality that I know of here. Maybe in some special regimes, but.
Okay, yeah.
Sir,
Yes.
So density is constant here, only changing is noise, right?
Here we're just simulating the V equation.
Okay.
With noise.
Okay, so there are two kinds of noise, translational and rotational, right?
It's additive noise on the velocity field. That's all,
Okay, okay, thank you.
with white correlated noise, not so strong, in fact. Yeah, nothing. You can do whatever you want. I think whatever noise will destabilize this. This is to convince you that this is a nucleation process, etc. Let's skip this. Now, back to Vicsek. Okay, so Vicsek, particles. Okay, and we have put a little obstacle in the toner 2 liquid here. Okay, look what happens. Same coloring as before, except that the intensity of the color is density. You see that this little obstacle here has managed to nucleate a countergoing object which grows ballistically in time and reverses the flow. In fact, after some time, you may recover the toner 2 phase going the other way or not. In fact, if you look at a much larger system with a small obstacle, same size actually, this obstacle is the minimal size for this parameter is about 10 interaction lengths. So it's not so small, but small. And this is some thousands. Matter. This is a nice movie you saw at the beginning. You can see the presence of these bands which were nucleated by the obstacle and pass by again the obstacle because of periodic boundary conditions to nucleate some other bands, etc. And this never repairs itself. Never, never, never. So in a large system, if you put a small obstacle of totally negligible surface in the large system, this kills the toner 2 phase. Okay? Now you ask yourself, okay, this is an obstacle. That depends also on the rules that you decide. You have to decide the rules of collision with obstacle, of course. And only certain rules do it, but the rules that correspond to active particles. So if you are an active particle, I have an axis, I bump into this, and I will not reflect immediately. No way. I will keep my polarity and try to escape this way, okay? That's an active particle. If you implement rules like this to interact with the obstacle, you'll see all these things. If you say, oh, my particles reverse instantaneously their velocity in some kind of reflection, as if they were not active particles, then you do not see this anyway. So the next question is, if I don't have an obstacle, but I just put a perturbation in the system, because I don't want to wait for it to happen, I will put a bunch of extra particles locally going against the toner 2 fluid. Okay, what happens? Well, what happens is exactly what I showed here. I don't have a movie here, but what happens is that this initial blob of particle, localized, small, against the flow, can generate this countergoing object which invades everything. And then in an infinite system, this thing will grow forever. Okay. Now, in an infinite system, the probability of nucleating such a fluctuation, initial fluctuation, is not zero, maybe very, very, very small, but not zero. So it will happen here and there and here and there. And the conclusion is there is no such thing as a stable toner 2. Okay. Now, to be true, this is only happening in about half of a toner 2 phase. So let's put an extra line here in the middle, more or less, more or less. So here, it's metastable. So liquid is metastable. And here it seems, so far as we can tell, and we have some analytical understanding now, but here it seems stable. The liquid, the toner 2 liquid. All right? If you put the obstacle, it's spectacular. If you put the obstacle in what I call stable here, this does not happen. Flow passes around nicely. Okay, so now we have 1 hour for quenched disorder. That's very good. Unless there are other questions.
So is it active fluid or is it the normal fluid that we are having?
This is Vicsek simulations.
Okay.
Today I almost only show Vicsek simulation. Vicsek model. Here you have whatever, some millions of particles. And the color coding is, color is orientation, and intensity of color is density, so, or momentum.
Okay.
So what you see is the dense ordered regions, and the gas is black, basically. Okay, I can watch this forever. This is to convince you that indeed it is asymptotically disordered. Okay. Yes.
I have one more question. Can you cite an example in the real world for the kind of simulation you just showed right now? Will there be an example in the real world?
An example in the real world?
Yeah.
No.
No.
I mean, you know, it's so simple that, again, there's probably almost no real system that does this. But it's so simple that most real systems with alignment, etc., should also, you know, their behavior will be related to what you see here. You know, it's like, you know, why do people study the Ising model? Why? Yeah. If you know why the people study Ising model, then it's the same thing here, more or less.
Okay.
You happy with this answer?
It appears that the front has characteristic velocity.
Yes.
Yeah.
The velocities of the bands are almost always near the nominal speed of particles. Not exactly. Sometimes larger. You know, the ballpark is there. But again, the speed, the V0, does not matter. I don't know of any phenomenon that depends on the speed, really. Some people claim so, of course, but they're wrong, I think. Anyway, so I will stop this.
So,
yes.
So can you go back to the slide of metastability of constant density flux?
Yes.
Yeah, the
slide.
simulation, can you please?
Yes.
Yeah. Is it the particle density that we are like looking at here, or
there is no density, it's constant density. So there's nothing to look at. This density has been taken out of the problem.
I didn't get like what is this color, these colors?
The color is the orientation of a velocity field, which is the only velocity. Now we simulate, let me go back to it. I'm not sure what it is, but we'll find it. Okay, we simulate this, okay, in which rho is a constant, so this is gone.
Okay.
Okay, this does not exist. This is a constant, and that's it. Everything is nothing depends on density. That's what we do.
Okay.
Okay, and we add a bit of noise.
Yeah.
All right. In fact, we simulate not even this. We simulate what you saw is without this and without this. If you put them back, it's okay. Doesn't matter. Doesn't change anything. If you put other terms, it doesn't change anything. So you need this, viscosity here, and a noise. Okay. And you see a V field, which has an orientation and a modulus, and what is represented is only the orientation. Okay.
Okay.
So density, that's the point. This is more fragile. So in this case, in the constant density thing, you only have one line. You know, there's no bands because the bands are coexistence. You have, you know, the gas, so to speak, or the disorder. And you have liquid, so to speak, which is order, and no coexistence phase, because the coexistence, the bands, etc., they really crucially depend on the interplay between density and order. If you're very dense, you're very ordered, and so on. Here, if you kill density, there's no such thing. So you have a direct transition. Okay. Mm-hmm. But this thing is metastable always. Okay. So what you have, in fact, is a gas of Astor, or form of Astor. let's call it aster form. Active aster form.
Oh, so there, if we just want to track one single particle, how can we imagine its trajectory?
So here, there are no particles in these simulations. If you do a lattice particle model for this, well, it is kind of ill-defined question because there's no density. So it's always, we have a lattice model of this in which each lattice side is occupied, okay? And the spin locally has different orientation. So, and it's hard to follow a spin in space-time because it's everywhere. So we have some rules in which you do exchange particles. So these could be followed, yes, and I don't know. Now the asters, they can be inward. The asters you see here. So the sign of the asters depends on the sign of lambda. Lambda can be positive or negative. Here you see that the asters that you see here, okay, these asters, so here are outward asters. So here you go out in the 0 light blue, go out. The pi, the red, you go in. So we go out, sorry. Everything goes out, so to speak. If you change the sign of lambda, everything goes in. It's actually completely symmetric, this equation, so it doesn't matter. Now, if you think of particles, typically, if this is really mediated by particles, this would be probably an inward aster. And then diffusion compensates the inward drift. And there are studies of these things. And you see asters of microtubules and things like that also. So these are typically trying to get in, okay? And then they're stuck because of steric interactions. But again, here, we don't claim any relevance to anything. It's just a general message that all these active, nicely long-range ordered phases are actually very fragile and metastable.
Okay, thank you, sir.
Okay, let's go to the other. I have to stop sharing this and share something else. Probably do this first. Let's stop sharing. Let's share something else. If I find it. Oh, yes. I spent in the plane, I added a nice, no, sorry, this is not what I wanted to do. I'll do it again. Yes, no, it was okay. This one. Yes, but I don't see it. I don't see it. Is that okay? Is this gonna work? No. I'm back to the other one. And this one. Okay, goes this one. Sorry. Yes. All right. So this gentleman, Yutuan, actually these slides are based on a talk by him. So he had this probably very nice AI generated picture of a flock of whatever on some complicated terrain. So there's complex environments, okay? So today the complex environments is just what happens to the Vicsek model if now the medium in which the particles move is disordered, weakly disordered. Okay, it's strongly disordered, like you put an obstacle, like I just showed you, you can already have dramatic consequences. Now the difference is, now we put disorder everywhere, but very, very, very weak, okay? And the question is, can we break everything with arbitrarily weak disorder? The answer is yes. So, yes, these two gentlemen also contributed. And it should work this way too. Yes. So, since we have a young audience, so quench disorder is a famously hard problem in equilibrium StatMech, okay? And many things are known. For example, if you take the ON, so-called ON model, for which the Hamiltonian is just Ising-like if you want, but with spins which have n components. So n equals 1 is the Ising model, n equals 2 is the XY model, Heisenberg model, etc. If you do this in some d-dimensional hypercubic lattice with summation over the lattices, and so you have coupling constants, Jij, from neighbor to neighbor, and maybe some external field Hi acting on each site I, okay? Many things are known. You can have different types of quench disorder. For example, you have random couplings or random bonds or random temperature. For example, random couplings here, the Jijs are positive, but they are distributed around the value J0. And the field is homogeneous. This is one case, or actually or 0 or no field at all. You can have random couplings. You can also have random fields, so homogeneous coupling constants, so like the pure case, like the Ising XY case. Okay. But random field on each side with a 0 mean. Okay, so this influences the ordering of spins. Okay. So what is known is that random couplings, sorry. Yes, I skipped one page. Yeah, so the pure case is all the Jijs are J0, and there's no field, of course. Okay, now what is known is that random couplings have no qualitative effects on the ordered phase, but they may change the phase transition, but that's another story. And arbitrarily small random field disorder kills the ordered phase in dimensions smaller than 4 for systems with continuous symmetry, meaning n larger than 1. So this is a case where arbitrarily small random field breaks totally the order. Okay? So the first lesson here in equilibrium is depending on how you put quench disorder, you get totally different answers. Okay. And random couplings can be seen as a weaker form of disorder than random field in this context. A remark here is that 2D random field XY, which is something like we should be thinking about now if we want to consider 2D Vicsek with some kind of random field disorder, that will be the reference point in equilibrium. There's no ordered phase, okay? All right, so that's a few facts about what is known in equilibrium. Another important concept, even in equilibrium, is whether a system is self-averaging or not under the presence of quench disorder. So you can define many different samples of disorder. So the way you decide of your random variables, which are fixed in space, you can do it many ways. Do the statistical properties of a system depend a lot from sample to sample, the sample having the same statistical distributions of spins or fields or whatever, couplings of spin. So the order parameter values that you measure depend on the sample, but how do they depend on the sample is a good question, okay? So here, so a sample here for the random field ON model would be a given distribution of the HIs, okay? You distribute them with some Gaussian, whatever, with a mean 0 or whatever, something, but depending on the particular realization of this distribution on each individual spin on the lattice, you may ask yourself, how does the order parameter, global order parameter that I measure, magnetization here, varies on the sample? Okay. So the values of M that you measure for many samples, they are distributed with a mean M and a variance Vm, okay? And the system is self-averaging if the ratio of this variance over the square of the mean goes to 0 as you increase system size. You increase system size, the sample-to-sample variations decrease, okay? And of course, you have cases where the system is not self-averaging, so that does not go to 0, okay? It's non-self-averaging. And of course, if your system is not self-averaging, which you can measure, then of course, life becomes very, very difficult, numerically for sure, and also analytically, okay? These are famous references here, but this you can find in many places. Okay, now, what about, another important concept, sorry, reading the slides one by one, is ergodicity breaking. The phase space of a given model may break into different attractors in the presence of disorder. So you'll see this more clearly later, but so again, with the ON model in n larger than 1, if you have random couplings, the global rotation, which is a soft mode, usually in the pure case, also it remains true. So here you have no ergodicity breaking in some sense. In a random field case, on the other hand, the system is not rotationally invariant. The global magnetization is fixed by the disorder. But then you have no ordered phase, so it's hard to conclude. Anyway, in equilibrium, usually you keep ergodicity. That's what, if you have an ordered phase. Now you'll see in the Vicsek model that this is important. Okay, so there are some previous works on the effect of quenched disorder on so-called polar flux. We have our friends Toner and Tu here. Okay, what did they do? More or less the same thing as before, except that now the noise term that they add to the equation is only dependent on space and not on space-time, okay? So it's some kind of random field. This is some kind of random field noise because you have the V field or influenced by a local direction of the noise, so to speak, local in space. This is random field disorder. And their arguments, their chain of arguments concludes that in 2D, the long-range order of a Toner two-phase would become a quasi-long-range order, meaning correlations decay algebraically in space and time, okay? Perouani and company did some poor numerics on continuous time Vicsek model in the presence of scatterers like this. This is actually an experiment. I should start with Bartolo, but let's go. Okay, so Bartolo and company with the Quinker rollers managed to manufacture samples, substrates in which they have obstacles at random positions. This is an experiment where the Quinker roller here has come this way, I guess, and has been scattered by this fixed obstacle here. You see that there is a deviation angle. It really, this acts really as a scatterer, okay? So they did experiments and they concluded that you should keep some kind of long-range order. I mean, it's a confusing message, but anyway, from the ordered phase of the Quinker rollers. Okay. Perouani did the same, the Vicsek, continuous time Vicsek model, dilute scatterers like this. And their conclusion is, again, a mixed message that you have a long-range order somewhere for weak disorder, but then if it's strong enough, you have quasi-long-range order, but none of this is really convincing. So anyway, they are not compatible with each other. All of this, of course, the system size remain relatively small. Nobody seems to care about sample-to-sample fluctuations. Nobody seems to care about the different types of quench disorder making a difference. And of course, in the case of Turner 2, this is only perturbative arguments. So given what is known in equilibrium, this is a very poor state of affairs. And so we decided to try to do this seriously. It turned out to be difficult, but so what we do is we take the 2D Vicsek model, and we add random quench variables that are defined on unit boxes. So we partition the space into boxes of size 1. 1 is the interaction range. Okay. So on each box, you define something. So you can define, for example, a random coupling-like thing, meaning you have on each box, you have a certain level of noise. What was called eta before is now eta I, n, depending on the box n in which the particle I is. So this is written here. Here you have a particles j is around I. You calculate the average orientation. Then you rotate. This is an angular noise. You rotate particle I at time t by an angle eta depending on n. So each box has a given angle assigned to it by which it rotates the particle. A strength of noise, sorry, not an angle. This is the strength of a noise. The strength of a noise depends on n. N is the index of a box in space where the particle I is on currently. Okay, so it's a landscape of noise levels, which corresponds to a landscape of coupling strength between the particles, because these things are. Do you understand this? So random landscape of noise levels instead of having homogeneous noise level. Okay. Another case we did is we called random scatterers. So here what happens is that we do the same thing, we do a Vicsek thing, okay? You have a noise, but you have an extra, the usual noise, given noise strength eta, homogeneous in space. But you have an extra rotation by an angle epsilon, depending on each box n. This angle epsilon is a random angle. So if epsilon is small, it's a small angle that you add to the final angle you calculated. But that one depends on the box you are sitting inside. Okay.
And is this epsilon a function of time, or?
No, it's a new parameter.
What I'm saying is that the strength of the noise, is that a quenched variable or is that an annealed variable?
This is a constant. It's a new parameter. Okay, it's a uniformly drawn between minus epsilon pi and plus epsilon pi, the extra angle. This is what is written here. It's not okay. So you do the usual Vicsek thing. When you have calculated your mean angle, added a random noise, you add an extra angle, which depends on the box you are in. Okay, this angle has an amplitude epsilon. Okay, epsilon equals 0 is Vicsek. All right. Sorry, I went up. And again, also in the random coupling case, in fact, this noise level in the box n is drawn between eta and eta plus epsilon. You don't want negative noise, that's why we do this. So that when epsilon equals 0, it's also Vicsek. So epsilon equals 0 is Vicsek, and epsilon is the only new parameter here, which is one advantage compared to random scatterers, because random scatterers, you have also a typical length scale in between the scatterers. Here we have homogeneous quench disorder, so to speak. Okay. So it is a Vicsek model with the usual two parameters, density and noise, plus an epsilon, which measures the strength of quench disorder. And we have essentially looked at two types. we looked at more, but I won't talk about them. So something like a random coupling, and something like random scatterers, which actually behaves very much like random field. Hello, hello, welcome. This is work by one of your postdocs, I mean, before he joined you. Okay, so we have these two types of quenched disorder, which is a single new parameter epsilon. Okay, this is a frozen landscape of noise strength, as I said. And these random scatterers deviates particle by some extra angle, extra random angle. This is similar to random field. Now the question is, what does this do on Vicsek things? Okay. Now you have, the answer is already at the level of phase diagrams, simple phase diagrams in finite size systems. This is a noise strength, a usual noise strength, okay, like in Vicsek, the same one. And here the strength of disorder, epsilon. You see that for random couplings here and random scatterers there, these very different looking phase diagrams. This actually looks like a Vicsek phase diagram where you have a polar liquid. Sorry, this is dead. Okay, no more pointer. You have a polar liquid here at the bottom left, and some bands, coexistence phase, and some gas above. Okay, whereas in the case of random scatterers, these things look very different. The polar liquid is labeled onto different color. You understand why later. Very different, and the shape is very different. And so already a signature of very effects of types of type of quenched disorder, depending on.
I have a question.
Yes.
Does it in any way resemble the spinodal decomposition, the right one?
You mean on the right hand side?
The diagram on the right.
Yes. Well, no. I mean, this looks like something like this, but it's just a shape. Here, these are two noise variables. There's no density, so density is fixed.
Okay.
Change your battery or change the pointer.
Change your pointer, maybe. So they have, yeah. So let's try this. Here.
Oh. So this one here.
So this is the cannon. This is the one.
Okay, that seems to be working. Where are they? What is this? Uh-oh. This is pointing, but this is not moving now. So I'm not sure. Okay. Anyway, this is not.
This is not working.
No.
Can we try this one?
Or maybe we should do it again. Let me do this. Maybe we should get. Yeah. Yes. Come on, go away. Yes. All right. So there's no density here, so it's just a visual analogy if you want, but no, it's.
Okay. Yeah, thank you.
I mean, there are interesting transitions here, of course, but since we don't know yet what is this phase, it's very hard to talk about the transition. Okay.
Yeah.
So my problem is now to understand what are these phases. Here I said polar liquid. You'll see that it's something different than the usual toner to liquid. Here I see the bands and the gas, etc. But okay, let's go slowly through this. So this is just a rough but very clear indication that different types of disorder do very different things. Okay?
Yeah, thank you.
As in equilibrium, basically. First of all, again, this is complicated, and I don't think I will spend a lot of time explaining this, but the message is simple. In the band phase, you maintain long-range order in the presence of this quenched disorder. This is a very, these band profiles carefully averaged over samples, etc., fall on top of each other. at different system size. This is our best measurement or indication that you maintain true long-range order in spite of sample-to-sample fluctuations. So the general message here, but I don't want to spend too much time on this, is that the coexistence phase, the band phase, resists at least finite amount of quenched disorder. Of course, if you put very strong disorder, you break everything. That's clear, but that's one message. Something more surprising. Now, if you look at the liquid phase, the toner 2 liquid, okay, you say you follow, this is a angle and time series in log scales. So here we start at the center of this disk. If you go radially, this is a log scale of time, and that shows you the global orientation of order from a given initial condition. So you take a system with this random disorder, you decide of an initial condition, for example, all the spins in a given direction that are initial, whatever, and you take here, whatever, 8 of them, 8 different initial conditions, each defined by different angles given to all particles on the same realization of disorder, and you follow what happens in time. If you start here with a green, so all the particles are going up, so to speak, and it stays there forever until 10 to a million time steps, basically here. If you do it, if you follow the gray, I think you have several gray ones here, 4 gray ones. You look at the gray ones are going all over the place. Gray is the pure case, no disorder. So in the pure case, global orientation is a soft mode, so it wanders in a finite system, slowly but surely, diffusively all around. Now let's look at, this is a random coupling case. You take the red one, it started here initially as given, then deviated and joined this 180-degree configuration. So did this one, also joined there. So did the purple one, which started there. So 3 of them went there, 2 of them went there, 2 of them went there, the orange joined the green, so to speak, etc. So, but these are special angles, of course, which you see here. At the long time, everybody is going to the left, everybody is going down or up, whatever, okay? Now, in the case of random scatterers here, what you see is that the same initial conditions also joined into 3 of them here, 3 of them joined this particular non-specific angle here, and 1, 2, 3 of them here joined this other 0 angle. Okay, so the message is, and this happens, irrespective of a type of disorder, irrespective of the strength of disorder, if your system is large enough, out of many, many, many possible initial conditions, you will end up in a typically small, much smaller number, or smaller infinity at least, of attractors for a given sample of disorder, a given realization of disorder.
So if you now take, say, a random initial condition, so where everyone is pointing.
Which is just one of them, yeah.
Sorry?
Random initial condition will go somewhere.
Yeah, so will it sort of break down into multiple groups depending on where it was in the...
it depends on the sample, but typically you have a fraction of them going to one of the attractors. It's better to have an idea of how many attractors to use that sort of initial conditions here rather than just random. But if you do many random initial conditions, they will go to different attractors. That's how we discovered it, actually. First of all, you always spin the global order, whatever its strength. whatever the strength of disorder. So it does not wander anymore. Not only that, but it always goes to the same. So this is typically an active effect, so to speak.
So to speak, the order here is then much more robust than what you would expect from the naive donor tube, right? Because it is always going to the same orientation.
Yes, this is still at finite size, and it's not clear what asymptotically you get in terms of order. I mean, here it's for that sort of size, you go to a well-defined order, yes. That's the direction of order, not the magnitude of the order parameter. That's another story. And I'll come to this just next, I think. So here you see that in this case, random scatterers, the attractors, these are long time averages in the steady state of what happens here, basically. You see that you have, again, the color is orientation and the intensity is density or momentum. You see that you have large streams, various angles. These are clearly governed by the box dimensions, etc., in the weaker random coupling case. But in this random field-like thing, you have non-trivial attractors, so to speak. This is more of the same. Here you see the time series directly along time here. The gray is a typical pure system at size 512 squared. And these are, this is a very long simulation. This is what 10 to the, whatever, 6 or 8. You see here that you go to these very well-defined angles. These are the regular ones, and here the non-trivial ones. This is some statistics about, you see, you have some samples which do not reach a steady angle, which are wandering irregularly, but the fraction of these non-steady samples, or real disorder by disorder, some of them at small system size, almost all samples wander. I mean, the global angle is not pinned. If your system size increases, the fraction of these non-steady samples basically goes to 0. So you are left with, these are the 2 attractors and 3 attractors and 4 attractors kind of samples. But this is poor sampling because we don't know really. It seems to be the number of, here we go to 4 in this simple case because you have the 4 dimensions given by the box. In this more interesting case here, the non-steady ones decrease to 0 also slowly, maybe more slowly, but they do decrease to 0. And then you have more and more, 4, 3, 2, 1. It's not clear asymptotically how many you have. What is clear is that you have none that in which the global angle continues to wander. Okay. In the disordered phase, so, over there, I add my quenched disorder. What we see is that all initial conditions flow to the same long-term attractor. This is one such thing. This is a long time average of momentum, which shows you that, and this is, of course, depending on the sample. And it is explored by all initial conditions. All initial conditions flow in time to this general attractor. You can measure this by some Edwards-Anderson-like parameter, which measures the similarity, the way you deviate from time, t to t plus t. And you see you go to a small but finite value here, which means the system has memory always of a sample, of a disorder, okay? But all initial conditions go to the same. So you have ergodicity. This is more or less exactly the contrary of what Bartolo and company claimed. doing experiments where they have a given sample, because experimentally anyway they don't have hundreds of samples, but they start the system many times to different initial conditions, and they say, each time I go to a different attractor. I think it's wrong. At least in this Vicsek model, it is clearly wrong. It's true if you only look at what happens after a short time, too short for the initial condition to have reached this well-defined single attractor. So you keep always memory of the sample. This value here, the Edwards-Anderson parameter, depends on the sample. And whereas for the pure case, this is basically zero. So you see a clear. So asymptotically, you have a disordered flow, but if you look at it on long enough timescales, averaging over it, you see that it is influenced forever by the disorder, underlying disorder, whatever the strength of disorder again. Now, the more difficult case, and maybe the question that most people have looked at before, is what happens to the toner 2 liquid phase, okay, the presence of disorder. So we just show that you have, of course, dynamical fluctuations for the polar order as a function of time in a given system for a given sample and given initial conditions. Sorry, I keep pressing the wrong button several times this time. You also have, for a given sample, attractor-to-attractor fluctuations in principle, because you have many attractors. And you have sample-to-sample fluctuations. So this, in principle, allows you to, or forces you to define 3 susceptibilities at least. This one is mostly recording. So the coding here is that the bars here, the angle brackets is time averaging. The attractor averaging is, where is it? I'm confused now. The sample-sample fluctuations is a bar, and the square brackets is attractor averaging. Anyway, you can define, so these are classic susceptibilities defined by people working on these things in equilibrium. This is dominated by dynamical fluctuations. This is dominated by sample fluctuations. And this is a new thing that we, in principle, have to consider, even though it's hard for us to measure anything there. So we look now, what we're going to do now is we look systematically at, for a given system size, given parameter, for a given sample, we look at many different samples. For each sample, we look at different attractors. And of course, for each of them, we average over time. So numerically, it could be a nightmare. So the conclusion of this is that, okay, sorry. In the random coupling case, which is this weaker form of disorder, you have self-averaging in the sense that the susceptibility, is particularly the sample-to-sample susceptibility, is weaker than the dynamical fluctuation susceptibility here, and they all decrease with system size, the exponent close to 2. This means that asymptotically, everything is self-averaging. So in this case, you don't need to average over many samples, and you just take a large system and it's fine, okay? Now, in the case of random scatterers here, random field, what you see is that the green one, the susceptibility increases with system size. So it's not that, so this is the worst possible case for non-self-averaging. You increase your system size, and the fluctuations of what you measure from sample to sample get worse and worse and worse and worse. So your numerical life becomes horrible. If you want to study large systems, you need to average over many more samples. So does the attractor actually susceptibility, so you need also to average over more attractors. And this is typically in equilibrium problems and others, in statistical mechanics, a case where there is no ordered phase asymptotically, because asymptotically you see that the dynamic core susceptibility here, connected one here, decreases, sort of decreases. But then the total susceptibility, which measures the sum of these things, decreases with this one, which dominates at small size. But then at large sizes, this is starting to be dominated by the sample-to-sample fluctuations, meaning all the fluctuations are completely governed by sample-to-sample differences. And this usually is accompanied by the breakdown of order. So, so numerically, of course, this becomes very difficult. And here, about order itself. So here you have a measure of the fully averaged magnetization, a polar order, average over time, average over samples, average over attractors. Okay, in the pure case, this is toner 2, it decreases like a power law to some constant, like we saw before. Okay, here is a measure of a local exponent of these log-log plots, sigma. You see the minus 2/3 that we saw at the very beginning today. You know, remember this discussion about how do you go to a constant? You go like a power law of an exponent 2/3. This is it here. Okay, so that's long-range order. In the case of random couplings, you see that it decreases, it seems to go also to a constant. If you do the same analysis of this data here, which you do not see very well, but you measure the local slope of this curve, you plot it here, you see that the beginning starts at small system size. It starts like the toner 2 thing, and then crosses over to a much faster power law, but still pretty much straight, from which you can conclude clearly that you have long-range order, even though you have quenched disorder. But this long-range order is very different from a toner 2 disorder. Okay. First of all, the angle does not wander, as we saw. Actually, sorry. The angle wanders for small system size, and at about that size here, crossing over between the two behavior, this is when typically your global order stops wandering. Okay, so this weak form of quenched disorder preserves long-range order, but it is a very different long-range order from the toner 2 thing. Now, in the random scatterer case, which is this one here, this dark red, you see that, okay, it seems to decrease more or less straight, which would be quasi-long-range order. But then it turns around here. There's a bit of curvature down. I don't know if you see it. I see it. If you look at the local slope, it does decrease and it's almost flat. But then it goes up, which is this curvature here. So this is statistically significant. It is not quasi-long-range order. And if this continues, this goes to disorder. This is the case where the sample-to-sample fluctuations from here, basically from that sort of sizes, start to be dominating. Okay, more data on this is here for this random scatterer case for different values of epsilon, including very, very small. You see that, what do you see here? The sample-to-sample fluctuations at the beginning here for a super weak disorder do nothing, but then start picking up, then pick up, then pick up, always with more or less this power law. So the sample-to-sample fluctuations seems to always increase with system size, however small the disorder, however weak the disorder. When it does this like this is because here you go into the disordered phase, basically. And you see that the exponent, that's the local exponent of the magnetization versus system size curve. This goes to 1, meaning it goes to the disordered phase. The one we looked at before is this one, I think, when it starts picking up, picking up, picking up, picking up. And here you don't know, but it's because this is starting from much lower here, but picking up the same way if you extrapolate. should eventually dominate. So the only decent conclusion of extrapolation of these already very expensive numerical results is that eventually the whole phase will be destroyed by the sample-to-sample fluctuations, so-called strong disorder fixed point.
So for some of these cases, it looks like that the susceptibility sort of increases followed by decreases as a function of sample
it
size.
decreases when it reaches exponent 1 here, meaning you have passed into the disordered phase where everything is the exponent order is decreasing very fast with,
I see.
and
Okay.
then you become again self-averaging, as I said before.
In the disordered phase. I see. Okay.
So again, you know, this graph probably is about 1 century of CPU. I didn't say 1 year, I didn't say 1 decade, I say 1 century of CPU. So beyond that, it's ridiculous, come on. The problem is these systems where obviously sample-to-sample fluctuations dominate. These are really very hard to treat numerically, obviously, but also analytically. The only people who do this, specialists of this, is Thomas Vosta, and then the so-called strong disorder fixed point RG viewpoint on this. But the conclusion is always that the asymptotic nature of a phase is a disordered phase, totally dominated by the disorder, however weak the disorder. Okay, so this type of quenched disorder on the toner 2 phase destroys it completely. The other type of disorder, the random coupling, is weaker, but changes the nature of a phase. It's still ordered, but very different from toner. Okay. And next I had what? Some kind of summary, yes. So what we did is here in red, random coupling, the weaker form. It has some long-range order in the liquid, but it is qualitatively different from the pure polar liquid. In particular, it doesn't wander anymore, and you have a much faster approach to long-range order. It is self-averaging, and nevertheless, it still breaks. You break ergodicity, but the 4 attractors you have along the directions of the box are statistically identical attractors. So, you know, they have no attractor-to-attractor fluctuations. The random scatter random field, we also did random field. In fact, they do the same thing. You have something which looks quasi-ordered at finite size, but analysis of sample-to-sample fluctuations, like we just saw, leads you to conclude very, very likely asymptotically completely destroyed phase. No self-averaging, that's a key. And ergodicity breaking plays a big role also, because attractor-to-attractor fluctuations also increase. Okay, now this is to be contrasted with what was said before. You know, nobody here spoke about self-averaging or ergodicity breaking, which is, at least for self-averaging, very, very surprising. And basically, we disagree. Now, you can say we disagree because we look at a specific model and they didn't look at the same model. I don't think so. Okay, that's where we are. But the general lesson, at least for the Vicsek model, is that any type of quenched disorder qualitatively changes things, somewhat dramatically for this one, completely destroying order. And less so here, but giving something that we don't really understand, also long-range order. Okay, and there is a general conclusion. Yes, about spatial disorder. I already said things, you know. You lock global orientation immediately. So already you see that you are away from the pure case. Ergodicity is broken, which is surprising and should be understood better, but okay. And different types have different effects. Numerical work beyond that, or 3D or whatever, you know, not reasonable. 3D we tried a little bit, but you know, because 3D toner 2 predict long-range order in 3D, even in the presence of random field. While from the pure small 3D systems we run, we can see that it's probably not true, but what it is that we see, we don't know. So, and yes, so we need theory. And of course, theory in that sort of context is very hard. So you can read about this in this paper, most of these results. Yes?
Many of the analysis of random field systems, so for example, random field Ising model, etc., can be done at the mean field level. So does the mean field calculation is of any help in this case?
I don't think so. No, I don't think so, no. But depends what you call mean field also here. No, I actually don't know. But,
so like assuming, so typically like in the random field Ising model, you assume that all the spins are interacting with everything else. And that gives you...
So if you do this here, you are falling back into random field Ising or XY.
Right. Okay.
Yes.
So
I mean,
that
globally coupled is no space. The thing here is space, neighbors, and changing neighbors, so to speak.
So that's what is. So the changing the topology becomes important. Okay.
Thing is that, you know, the particles, they flock. Imagine the infinite system, and they always visit new territory. So this is a very different problem from being fixed at the nodes of some disordered lattice. But then if you go to the globally coupled limit, all this boils down to this. Yeah. In some sense, you say 2D random field XY is disordered. And this is also our conclusion. Whether it's the same sort of disorder, I don't know. This is a set of results where the numerics is very heavy, not very difficult, but very heavy. So depends on your level of, you know, rigor. You can publish half-cooked results like Peruanian company, and if you look at them and compare what they do to what we do, you'll see what I mean. But then beyond this, we're stuck, you know. And at the theoretical level, you know, given that we already have problems with the pure case, a good theory on understanding of a pure case is not quite. Yeah, so.
To understand, say, flocking in the presence of disorder, which is kind of ubiquitous.
Yes.
So then what is the way out then?
Right now, I don't know. You need, I know, some RG methods, renormalization group methods, can deal with non-equilibrium and disorder. So this is so-called non-perturbative RG or exact RG. So people like Gilles Tarjus. There are a bunch of people, most of them in Paris, actually. So non-perturbative RG or exact RG and various names, depending on who you talk. And so on the non-equilibrium side, you have people like Delamotte, okay, myself and others. That's non-equilibrium, StatMech systems, and people like Gilles Tarjus, Mathieu Tissier, these people also, all in the same lab in Paris for disordered system using this method. Okay, and using both non-equilibrium and disordered systems. This guy started a bit, but they're not very far. But normally the method is able to deal with that sort of system. I think this is the only promising way. Of course, there's a price to pay to enter the method. But numerically, I think we're doomed. So.
Very, very naive question, mostly for the first part. Like when you have this, when you do this numerical experiments with these bands and forming, so I mean, how long do you run the simulations and like how can you say that that is like for very, very long time, these are like very stable?
For the bands, typically they form very fast. Okay. Thousands of time steps. But then for them to reach some kind of steady state. So first of all, for a long time, if you look at my own papers, for a long time, we wrote that these things coexist at arbitrary locations, that are really independent, solitons, whatever. So these were the times where we were looking at things over, 10, 100,000 time steps, something like this. To see the movie I showed you where you see the 7 bands equilibrating, this needs millions. And we did that only because progress in the PDE analysis, showed clearly these periodic solutions and all that. It has to be periodic, so we run the simulations longer. And indeed, it is. So this is where, then systems of bands crossed, or these exotic things that I showed you. Now we are at 10 to the 8 weekly time steps. And systems which have grown in size also for reasons I showed you. I'm not sure it's the end. Because we don't know the stability, along the band. Suppose now, which we are making now an effort. Now we are looking at bands analytically, single band, and try to get an idea of its linear stability seriously. And also numerically, so now we are talking, I showed you bands at the beginning were 100, and then 1,000, and then 10,000. Now we're 100,000. And we try to look at this problem in terms of roughening, etc. And then, of course, the next steps would be maybe 2 bands in interaction, because they're always in interaction, more or less. And then the stability of the spectic. So, we don't know. If we do find that even a single band is unstable or roughened so much that, then, okay, asymptotically, you can throw out everything and it will be a disordered. It will be disordered here, That's it. And plus the fact that the total to liquid is metastable and very fragile, But come on, it's only almost 30 years of study of the Vicsek model. People still find interesting things to say about the Ising models. Still young. Anyway.
So this is.
All is simulation based. Are people also doing experiments on like similar things right now?
People are trying to do experiments, and again, these systems that are experimentally available where you have many objects moving and good control, you can look at birds, but that's all you can do, look at birds. Bacteria is a bit better, but they're in a liquid. The Quenched rollers is very good. Normally, it's complicated physics, but it's just hydrodynamics, etc. Complicated, but still. But they're also in a liquid. So you have, this charge instability is coupled to hydrodynamic interactions, coupled to friction on the substrate. It's a complicated problem. So it's a priori rather far from Vicsek. Okay? But there you have good control and you can have millions of particles. If you have a good homogeneous field. What people do, which was in fashion and still is I think is a good way to investigate active systems, is to use biofilaments, microtubules, or actin filaments and molecular motors, preferably in 2D, either a carpet of motors or motility assays or things like that. There you have very good control. In some cases, the filaments are strongly attached by the motors so that you can probably neglect the fluid in which they bathe. So these are good experiments, but it's not you know, some of them, it's mostly alignment because the two filaments meet and they collide onto each other and they align. Not always, but some of these experiments are like this. Some of these experiments are really alignment. A bit of steric interactions, of course, because they align because they touch each other, not because they decide to align. So these are good experiments, and maybe some of them should be revisited in view of all these things. Indeed, in the very early days, Bausch and Schaller had a paper very early 2010, I think, Bausch. Andreas Bausch, okay. In Munich. So motility assays with actin. Actin is a bit, when we saw things like bands, actually. At the time, actually, was not clear. Even the Vicsek bands were not that well understood. Then people said it's the same. Not very clear to me that it's the same, but maybe these sort of experiments should be revisited. Nowadays, they're relatively easy to do if you have access to motors. But, so there are ways to do this. And these may be most promising. Because the shaken granular things, it's okay. You cannot do very large, and then it's, you know, it's just a toy. If you look at the Quenched rollers, it's already more interesting. To what extent are they really described by Vicsek and Toner 2, like Bartolo claims? I have my doubts, but, you know, but these experiments are not so hard to do. Bacteria is nice, but many of them are in a fluid, and the fluid is important. Not always, but yeah.
Okay, very general question. Like, what motivated you to look so deeply into this very seemingly simple Vicsek model?
You know, it's statistical physics viewpoint. You know, you want to understand the simplest things. No further than this. I think it's a good idea. Vicsek had a good idea. You know, he was interacting with these people, looking at bacteria and etc. I say, you know, what is the simplest thing I can do? Okay, and the funny thing is that the simplest thing you can do is already so complicated. You know? So now imagine the not so simple things you could do. What is the truth? Right. So yes, that's my viewpoint. Always been. I'm doing other things than that in life, huh? But this is key. Okay? And it's also maybe not so much today, but it's a lot of work at the continuous level, at the PDEs, at the kinetic level. We simulate the Boltzmann equations and all these things. So this is also very interesting, but today it did not appear so much.
So maybe just one last question, okay?
Since you mentioned about the magnetization and the chi. So does this thing hold any relevance in the, say, magnetic transition from some paramagnetic to a magnetic phase or something like that?
You want to speak about renormalization? Is that
No, in one of the slides you mentioned about the magnetization.
Well, magnetization is the same word as polar order. It's measured because the order in Vicsek case, at least the order is polar. You know, all the little velocities pointing together. This is like magnetization. So sorry, I'm mixing the two words.
Okay.
Yeah. So, you know, in the context of Quenched disorder and StatMech, people speak of magnetization. Depending on the context, use equally frequently magnetization or polar order, but it's the same thing. For the nematic case, of course, it's a clearer difference. But yes, sorry for this. There's some M's and some P's or Pi's or whatever. All this is the same, you know, suitably averaged modulus of the polar order parameter or magnetization strength.
Thank you.
Right, then, in interest of time, let's
Yes.
thank Professor Hugues.
You're welcome.
thank you for like, I don't know if you know, he reached like at the middle of the night last night.
Yes, that's nothing.
All right.
Maybe this afternoon I won't be so cheeky. But
So we can stop the recording now.